Hi, this is Dr. Liu, and in this video I will go through the introductory lab, basically introduction to Microsoft Excel and some basic statistics. So let's get started. On the left half of the screen I have the right up. The right half of the screen is Microsoft Excel. So let's get started with the just basic Excel introduction. So this is a cell, and that's Excel's language. So the cell can contain anything between values, texts, and the formulas. So you refer to it by looking at the column and also the row. So this cell is a cell B2, and that will be an F9. All right, and this will be called a column B, and this would be row 10. So most of the times it's more convenient for us to organize data in a column, so we can refer to as the row 8 has what value, row 9 has what value. Instead of you go horizontally out, you say, well, that's I got column G, a column H, and then I have some values in column L. So how far down the columns is L from G? Well, you have to count that up. It's easier if you say, well, I have some number from row 4 and row 8. So row 4 to row 8, that's 5 rows. It's easier to count. So data mostly are organized in columns of many rows. Okay, so let's get started with the first procedure right here, part 1 with statistical analysis. So in this analysis, we have an example which is finding the gravitational constant near the surface of the Earth. So we have done measurements. Supposedly someone has done measurements, and these are the measurement values. So you're expected to enter these values into Excel and calculate average and standard deviation. So let's get this part started. So we open Excel, we start entering these into the first column, and we can label this column. This is the label is just text. I'll just type G with parentheses, meter per second squared. So it's always useful to label a column. It's required. You cannot just have a column that is not labeled. What would be column's content, right? Okay, so I'll go ahead and type up all the numbers, and I'll check once in a while to see I have the right numbers typed in. Keep typing in the wrong number. Oops. There. See, if I type 10.70, the trailing zero is hidden by Excel. So I'll tell you how to show that once I'm done with all the entries. Okay, so let me check the numbers. I'll zoom in. So 866, I'm just pointing with my fingers. 933, 969, 1112, 932, 1015, and 895, 969, 1043, 1070, 1107, 03, 814, 955, 1052, 827, 1021, 10 to well, 10 to 1 is already there. It's 1037, 871, 983, 971. Okay, so we got everything. So now I want to show the trailing zero. So how do I do that? And here's what I do. And don't try to go to that one specific values, because maybe there are other places you didn't really realize there's a trailing zero that's missing. So select everything. And since I have everything kind of hidden away. I'll just pin that. So there's this numbers ribbon portion under the home ribbon, and these are decrease and increase. So we'll just increase and decrease. So by doing that, we're forcing Excel to show a fixed amount of digits after decimal. So now everything has 2 digits after decimal. Okay, so let's keep following the instruction. So now we need to calculate the average, and calculating the average requires us to get a sum, and then we divide the sum by 20 because we have 20 data points. The row number 1 was the label here. Alright, so in here, I'll just type it in here. We start a formula by typing equal. So without the equal, if you type anything in, whatever it is, it's considered as text. Even if it may appear to be a formula, it will not be processed as a formula unless you start with equal. And the case does not matter. I think you just type that up, and you can click and drag instead of typing in the exact column. So A2 column A21, that is just the range you're summing, and then you close the parentheses and hit enter. So that's a sum, and well, I can just do that just to mark it up, and this is average. So that is equal to the sum value divided by 20. Instead of typing 194 here, which could change if one of these values were actually incorrectly typed, so you say equal A22. So A22, you can click it, A22. So that refers to the sum, and if these values were to change or to update it, and that sum gets updated, so is your average. So that should be how you do it. Okay, 20. Okay, so that is your average. And let's see, the next way to get average is to just call the average function. So let's have another average. Yeah, that should have the same exact value. So we can do an average and then select this whole range, A2 through A21, or A2 colon A21, close parentheses, hit enter. So okay, well, that is a slightly different value because it has a different number of digits displayed. Well, how many digits are we supposed to keep? Well, the sum is an intermediate value, so I don't really care. You didn't have to write these numbers down on your own, which means you didn't have to make any mistakes with more digits. But the final answers do have to have the right amount of sig figs. So let's keep moving forward with the next calculation. Here, after the average, we're supposed to calculate the standard deviation, and that is a description of the all these numbers. What is the average? Well, 972. So how are these numbers differ, or how do they spread out around 972? That is the standard deviation, STD or STDEV, and you can just call this function. You don't have to know the exact calculations. You just need to call this function and supply all of these values to the function, A2 through A21 with a colon in between. So now you get your standard deviation. And this standard deviation is an estimate of your uncertainty. So in physics, if you have repeated measurements, and the standard deviation serves as uncertainty of your measurement, but you can't really have these many digits. So you go over here and decrease the amount of sig figs until you have only one sig fig. The 9 is the only sig fig. Okay, so now I can tell you how many sig figs you can keep is to line up with this 9, which means you only get to keep one digit after decimal. So we'll do that, and one more. Okay, so do you want to do the same for the sum? You don't, because this is an intermediate answer. You don't have to apply sig figs to your intermediate answer. Although it ends up being just 2 sig figs, that means your intermediate, if you just keep 3 sig figs, that should be fine too. But you don't need to worry about that. So remember, the standard deviation should only show one significant figure, and then whatever significant figure it shows, the relative spot after the decimal will be how many sig figs you can show with the average. So the last digits kind of line up between the STDEVs and their averages. Okay, so now you have gone through procedure 1, parts A through D, and now you want to assess whether your experiment, or the sum of 20 separate experiments, can prove the expected value. The expected value, according to textbooks and most references, is 9.81 meters per second. Oops. Okay, so it's 9.81 meters per second, and you want to calculate two things so you can see if you can get this proved. So one of them is called relative error. So relative error is you expected and you measured, you subtract the two, and if you subtract the two, this is called absolute error. So error is how far you got compared to where you're expected to get. So that would be one of these two averages, either one of them, subtracted from the expected. And we have an absolute value sign, so even if the subtraction is negative, you flip it to a positive result. So now that you have a difference between expectation and your measurement, you divide that difference by expectation so you can scale it as a percentage. It makes it easier to communicate across different labs, different disciplines. If you say I have a 3%, I have a 9% relative error, instead of I have this 0.9 meters per second squared relative error. Well, is that big or is that small? That really depends on that on top of what, right? So let's calculate this RE. So that's absolute value, although we don't need it, it's okay to have it. Expected, you click, don't enter 981 here. Since you already entered it once, you refer to that. So minus the measured and divided by the expected. So that'll give you a small value which you can format into a percent style of 1%. You could certainly say it's a 0.9%, but I don't really mind. This is an estimate of your relative error anyway. So now we have this and the relative uncertainty. So what exactly is relative uncertainty? Well, if you're doing measurements, you'll be uncertain because measurements come with uncertainty. It has nothing to do with what you're expected to get. It has everything to do with what kind of instrument you're using to get your values. So let's just kind of pretend that these values were obtained by a freefall apparatus. So that is going to set up your relative uncertainty. The apparatus is accuracy, right? So let's calculate relative uncertainty. And in here is uncertainty of the measurement divided by the measurement. Well, this is the measurement, the average. What about the uncertainty of the measurement? Well, in this example only, the uncertainty of the measurement is just a standard deviation because you measure 20 times, you got an average and standard deviation. But in a different lab, your uncertainty may be calculated differently. Maybe you didn't measure 20 times, you didn't measure multiple times, maybe you measure one time. How do you expect to find uncertainty? Well, each lab will have its own way to find uncertainty. Just don't use this formula. Don't use the formula I'm going to type up for every lab because this kind of only applies to this lab. So also we only keep absolute value. So this is the standard deviation is treated as uncertainty and divided by the average. So the value, uncertainty, amount of value over the value gives you a percent style. So you can just go ahead and cast this into a percent style, a 9%. Okay, so now it's time to draw a conclusion, and here's a nice diagram. A measured value here is our average, 97, and this uncertainty fuzziness creates a range of values that you're not certain whether you're getting 97 or you can get as low as 97 minus 0.9 is 8.5, and then you could get as high as 10 10.5, 10.6, from 8.6 to 10.6. So that's a range of uncertainty, and that range covers 9.8. So that's what this means. Your expected value is within your average plus minus your uncertainty. So you're uncertain whether you got here or maybe all the way here or maybe all the way there. So that is good enough to say that within your uncertainty you have proved the value. An easier way to say is if the RU is greater than the RE, you're more uncertain than you are. Then you erred. So then you can prove within your uncertainty. So this has to be greater than that. So I'll just say draw a conclusion because that is greater than this. 9.7 plus minus 0.9. Actually, let's I can't really quote another digit. The 9.8 is good enough because my uncertainty is high enough. So that is everything here for part 1. Okay, let's continue with part 2. So I just want to keep everything in one spreadsheet. This is my sheet 1. If I double click here, I can just rename this as part 1, and I'll create another spreadsheet and call this part 2. Okay, I'll zoom in again. And by the way, part 1 was actually kind of an exercise for our first actual lab, the free fall lab, and the part 2 is an exercise for our lost lab, a constant volume thermometer, gas thermometer lab, or absolute zero lab. So in this lab, we're trying to find the absolute zero, which is the coldest temperature. And we have some data here. So this data is kind of presented as 2 rows, but let's plot them as 2 columns. So we'll just name the column. You can say DEGC if you want, or if you find a way to insert that fancy degree symbol, that's fine too. But don't worry too much about the formality. It's the content, whatever you include, if it's correct, that's fine. You don't have to find that degree symbol. Pressure, the unit centimeter of mercury is kind of an old unit, but let's just use that. And see the columns are not wide enough to provide enough space, so I'll just select the 2 columns and double click the edge. See, now it actually auto scales both columns. And let's go ahead and enter these numbers. So the temperature columns are easy, 0, 20 with a 20 increment. So it's a good time to try and use Excel to automate the values. So to select a cell, you basically click the middle, right? Just like that. And in order to select a range of a cell, you click the middle and then click and drag. So this is a range of a cell. And now you see there is this green square box on the bottom right corner, and see my cursor looks like what? Looks like a white arrow, white cross with black borders. But once I approach this corner, now it turns into a black cross with white borders. Very, very difficult to see the white borders, but this is a special corner. If you click and drag, then it automatically fills the next cell's content using the first 2 cells or first several cells trend to fill up the 40. Yeah, there you go. So that makes it easier. This is only saving you from typing these values. But what if you have 200 rows of data and you need to automate some sort of label, right? That'll save you a lot of time. And the rest, you have to type them up. And you don't have to type the 0.0 because it won't display until you force it. So just forget it for now. Type in the values first. Okay, so again, select everything. This is how to select. Click the middle, and then you can select the range, and there you go. So now the 0 shows up. Okay, so now we have data. Let's see what we want to do with the data. So we enter into Excel, and we want to determine a fit. What actually that does is we'll keep going until we get to that part. So select the data for plotting. So what we want to select is this range of data. We are using temperature as the horizontal axis and pressure as the vertical axis. So click and select the entire 2-column worth of data. And then you can go to insert, and there's the charts ribbon section, and you can go for that. That is scatter. So drop it down, and we're going to go for that. We don't have anything in between, so there's no point drawing lines or curves in between. We just basically don't have data. Just click that. So I guess I need to zoom out a little. So here's our plot. Alright, and the plot is quite basic. It's not complete yet. We're going to have to find all the elements, add them in. So just go over here and click on this greenish cross. So you want to check the axis label. You want to check the legend, so you know what's what, and then you also want to check the trend line, and this gives you this dotted line that it fits through the data point. Okay, so back here, this is the horizontal axis label. That's a vertical. You may be tempted to double click and start typing, but there's already these column labels. They serve as these labels just fine. So you can click here, single click, and then press equal. See that equal shows up, and then the horizontal label should be just that. So you click this. So you assign the label's content to the content of the cell and hit enter. Now it gets connected, and single click there, type equal, see that equal sign, and click this label and hit enter. So now they're connected. You can certainly rename this. For instance, you can say pressure versus temperature if you want. So that's good. Alright. So let's see what else we need. So find the best fit line. We already have added the line, and we didn't really adjust its properties. The line just came out, and because we let's see, because we checked the box. Okay, so now it's time to adjust the properties. So right click on these little dots where the line is. See there, format trend line. So now we have this side panel coming out. Just make sure it is linear, and I also want to check display equation. We need to know what equation the line is drawn out of, and also display the R² value. And for this time only we want to draw our forecast backward, because we want to see where this line crosses the horizontal axis. So we can just throw in 300 units and hit enter. So now you can see, you can dismiss that side panel. So if you extrapolate through these data points all the way back here, you can see there's a crossing right here between the blue dots and the horizontal axis. So let's move the equation out, and okay, that's good. The vertical axis is pressure. So when this dotted line reaches the horizontal axis, that means pressure has dropped to 0. That only happens at absolute 0. So you want to know where this crossing happens exactly. You're going to have to calculate for it, but at least you now have visualized it. There's a crossing between your line and the horizontal axis. Alright, and this is the equation that draws out the line, and this R² value tells you how well these dots are fitted by a line. The closer it is to a 1, the better the dots actually can be represented by the line. So the 0.9992 is a pretty good indication that we got the right theory. The dots should be on the line. Okay, so we can just move forward and look at this for the next steps. So let's get back here and try to determine the value of this absolute 0. So we're trying to get this crossing, and then we need to do some analysis. Okay. So let's do this. So to determine the crossing, the equation is this. So the crossing means your y value drops to 0. So if this is your equation, when y value drop to 0, it should read this. 0 equals 0.2429 x plus 65.757. Okay, so don't worry about Excel trying to solve this thing, because I didn't start with an equal sign. It'll just be treated as text. See that? It doesn't do anything. Well, you have to solve this yourself. Then you'll be able to solve a negative x, which is the absolute zero value. So I can say x equals, this is just for the look. And now I actually want to start an equation. I want to calculate with basically negative 65 over this almost a quarter. So I'll type in the values first, and then I'll do a bit more complicated calculations to get these values from a calculation. So this is the crossing here, because we set the y equal to 0. So this line with the y equal to 0 is this point. This is where the horizontal axis is crossed. Well, I don't really know how many digits to keep though. Should I keep as many digits as Excel spit out randomly, or should I be doing 3 digits? Well, I don't really know. So I have to analyze the uncertainty in order to know how many digits to keep, and whether this is good enough to say that I proved the absolute zero. So I probably should put in the expected value. What is the expected absolute zero? Well, minus 271. Oops. There. So yeah, I have to know the uncertainty to see if that one with uncertainty considered is able to prove this one. So let's move forward to part F. Part F is linear data analysis. So let's do this. I'll select here. See, click the middle so I can select 2 columns and 2 rows. Alright, so once selected, I'll just type equal, and the function LINEST is a linear list fit. And then the tooltip says give your y's, give your x's, and some constants. Okay, the y is the vertical axis, which is pressure. So click and drag it here, B2 through B7. And the x is temperature. Okay, click and drag through here. And then you want to type a constant. Actually, you want true. And another constant. Okay, and the close parenthesis. So now you want to hold down to your Control and the Shift keys. And if you have a Mac, maybe it's Command and Shift. So while you're holding on to Command and the Shift, or Control and the Shift for PC, hit Enter. Okay, might have gotten something wrong here. Oh, I see. Okay. Okay, anyway. So if you want to change something, also Control Shift Enter. There we go. So what this is doing, you'll recognize, oh, that is the slope. And this intercept also shows up here. So what this function line is doing is actually calculating these two values. That's kind of a duplicate. If you thought about, you already were able to get these values, so what's the point of getting them again? Well, now these are the points. You have these extra things. So this below the slope is the uncertainty of the slope. You didn't get that from that fit. So go ahead and adjust it so that you only get to see 1 sig fig for the uncertainty. You can't really estimate more than 1 sig fig. So these two should have their decimals lined up and with 1 sig fig shown here. And separately have these two do the same thing. So the only sig fig is the 2 after the decimal. Okay, so now I'm going to label around it. You cannot separate this group of 4 because they came out together. So I'll just label around them. Slope, maybe I can move them out a little. Okay. Standard deviation slope, and this is y intercept. Right. Alright, since I don't have anything around it, this is okay. If I don't really like that too well, I can just scale that a little just to show everything. Okay, so I have just finished part F. This is a kind of a um, non-intuitive thing to do, is to hold down to a Control Shift and Enter. And again, you need to select 2 by 2, and don't select and then click again. Select it, and then you start entering the formula already just by typing the equal sign. All right. So if you're using a web browser version of Excel, it doesn't have this feature. So it comes out as 2 columns of 5 rows each. But that's fine too. It just tells you you should be installing the apps instead of running Excel through your web browser. All right. So now we have this. We can go forward to the next step. Okay. So here is the 2 by 2 slope, uncertainty, y-intercept, and uncertainty. So I'm marked around them because I can't move them apart. They came out together. So the relative uncertainty of absolute zero is calculated this way. Well, that's definitely not the same way as we did before in part 1, which was just relative uncertainty was just standard deviation divided by average. The relative uncertainty depends on your measurement, so this formula needs to be calculated. So let's go ahead and do RU equals, and that's just for the readers. So we'll start with equal sign, and there's a square root. We can certainly use square root, or we'll just use the power of 1/2. So ds is the uncertainty of the slope. I start parenthesis, uncertainty of slope, and divided by s, slope, there. Close parenthesis and square that, and plus open parenthesis dB, uncertainty of the intercept over the intercept itself, and close parenthesis and square that, and don't forget to close the parenthesis of the square root. So this is the relative uncertainty, and I can click this percent to get it into a percent representation. And let's calculate relative error. Relative error has the same exact definition. What is your measurement? What is your expectation? Subtract the two, the difference, then divide by your expectation. So equal absolute value. The expectation is this, and your measurement is this. You calculate it based on your fit. So that's this. And since we already have a negative expectation, I'll include that expectation in the denominator inside of the parentheses so that everything gets absolute value. So now it will come out to be a positive quantity. And I can also turn this into a percent style. So we can say they borderline proved it. If you don't like it, if you want to see, oh, okay, my uncertainty is a little greater than an error, so I proved it, that's fine too. But remember, these are all estimates. So soon enough, if you display more digits, you cannot defend those digits. So I can say RU is greater or equal to RE in either case of having 1 or 2 sig figs displayed. So okay, so that's good. That should be it. Thank you.